Test 1 2. Test. 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 1 2 1 2. Test 1 2. Test 1 2. Test. Test. Talking about SDR, yes. 1 2 1 2 1 2 1 2 1 2 1 2 1 2 1 2. I think that's good.
Want to start?
Good singing last one.
Okay. Okay, good evening, everyone. Why don't we get started? My name is Neil Pandya. I would like to welcome you all to the Cyberspectrum meetup. This event serves as a forum for the exchange of knowledge and ideas related to software-defined radio, and generally aims to get people interested and excited about the applications that can be realized with technology. Engineers, students, hobbyists, enthusiasts, and experience levels are welcome, no matter what your software or hardware background. At each meetup, people from the community have the opportunity to present their work, projects, and ideas to the group. The event tonight is being sponsored and hosted by Edis Research. Our first speaker tonight will be Kevin Reed, who will give a brief update to his talk, A Visual Introduction to DSP for SDR, which he presented at the very first meetup back in November. Tonight he will introduce new material about digital modulation and constellation diagrams. Our second speaker will be Matt Edis, who will give a talk titled Synchronization and MIMO Demystified. Beyond a single radio, there are multiple antenna systems, geographically separated systems, and all manner of multi-radio configurations in between. Matt is necessary to make these systems work, and the different levels of timing and synchronization involved. Our third speaker will be Martin Brown, who will give a talk titled The SDR Mythbusters. Is Cyberspectrum hard to do? SDR has a reputation for being very difficult, but is this actually true? Martin will give a tour through a typical development cycle and will discuss the tools GNU Radio provides to make development as smooth as possible. This talk is geared mostly towards enthusiasts who are looking to start their own GNU Radio development and who want to know exactly what resources are available. All meetup presentations will be recorded and posted online, as well as streamed live on YouTube. The previous 4 events have already been posted in full HD video. We have set up a channel on IRC called #Cyberspectrum Freenode.net as a way for remote people watching the live stream to contact the group here in Santa Clara with comments and questions. Future meetup locations will alternate every month between the Edis Research Office here in Santa Clara and Noisebridge in San Francisco. The next meetup will be on Wednesday, April 29th at Noisebridge, which is a nonprofit hackerspace in the Mission District. A list of speakers and presentations will be posted about a week prior to the event. If you have any ideas about topics for future talks and presentations, then please let us know. We would like to thank all of our speakers tonight for their efforts and their enthusiasm, and we would especially like to thank Edis Research for providing pizza and beer and hosting the meetup here tonight. So without further delay, let's get started. Balint Siebel will make a few additional announcements, and then we'll introduce our first speaker.
Thank you, Neil. Good evening, folks. Thanks very much for coming out this evening and joining us. Once again, have Now it's working. Okay, so they missed all that. Oh well. All right, so it'll work. It just has to go through the encoder. All right, so really, first up, we have Kevin Reed doing an update on his visual introduction to visual DSP. So very much looking forward to that. Pardon?
I need a new photo.
At least we know who you are. Next up, we have the Matt Edis, the one and only, essentially the father of commercial low-cost software-defined radio. And as you can see here, he's lovingly holding his very first amazing creation. So he's going to talk about some very exciting stuff where you take these and have many, many SDRs and make them do amazing things. And then finally, we will have Martin Brown. This was the amazing moment where at the GNU Radio Hackfest in 2013 at Virginia Tech, when he confirmed that his OFDM creation that he'd been working on for GNU Radio, the new OFDM implementation, actually worked over the air. So that was quite an exciting moment. Good stuff. And if you didn't quite see there, if you want to follow these people on Twitter, we've got @BroadCrap, @Switchborg, @Matt_rambling, and finally @Brown_noise. So they all do amazing things. So if you're on Twitter, definitely follow them. So that brings me to the end of my little bit. So Kevin, do you want to take the stage?
Okay.
While Kevin's setting up, I'll give a brief introduction. Kevin is currently a software engineer at Google. He is interested in building tools for better computing, specifically designing Okay, I took it from your LinkedIn page and a couple of others. Okay.
Do you want to give us the little spiel here then?
There we go. Testing 1, 6, 7, 8. Okay. So I apologize in advance. This is slightly poorly edited because I wrote it in a bit of a hurry compared to when this. Well, if you're going to do that, better move the table. Or you better move. Because Are we good? No, because I'm gonna be standing here. Okay. Give it a sec. Give it a second.
You can keep moving it that way.
Okay. Let's see. Okay. Where was I? Okay. So enough with that. Let's. At the first Cyberspectrum meetup, I gave my talk entitled "A Visual Introduction to DSP for SDR." This is purely the diff. This scenario. I'm going to be jumping right in, and so I hope you remember the lectures from the beginning of the semester. Yes, you have to implement this yourself. Let's see. It seems rather blank. My original talk was talking about digital signal processing. That is, signal processing as performed by a CPU or a dedicated digital computer of one sort or another. Now I'm going to talk about digital modulation. That is, signals which carry digital data. There, now I can actually see what I'm saying. So, digital modulation, signals which carry digital data. here we see a digital signal as you might see it in an introduction to digital logic. 2 levels representing binary digits, 1 and 0, 0 and 1, you know, and very sharp transitions between the two. Here's the simplest digital modulation known as on-off keying. For amateur radio operators, this is the CW mode, though this bit pattern is certainly not Morse code. You know, those things are different. You know, it's just, and this is actually, well, okay, to give a quick recap, here's the picture of amplitude modulation I showed back then. We can see that we have the classic picture of the sound wave and the carrier wave as modulated by it. But of course, we were talking about digital signal processing, which means we are talking about complex values. Okay, so if this still doesn't make sense, you know, I'm afraid you'll have to watch the video of my last talk. So this is actually identical to the amplitude modulation I just showed you, except that instead of the modulating signal being audio, centered about the level about +1, this is data, and it takes on the values 1 and 0. 1, 0. This is a very simple modulation to transmit and power efficient. You can just switch your transmitter on and off. That's all it takes. However, note that because of the sharp transitions in amplitude, this signal, as shown, has a very wide bandwidth at those transitions. Again, the amateur radio operators know those as key clicks. So, in order to fix the transitions, we use a pulse shaping filter on the modulating signal. This looks like a mess, and in fact, let's skip that bit. But it does minimize the bandwidth used, and it's actually very easy for demodulators to handle, as we will see later. Incidentally, the little notches you can see here, like these here, these are imperfections in the filter. We use a truncated filter, one with fewer taps, to save computation at the price of not quite being the ideal filter. The ideal filter is, in fact, infinitely long and therefore impossible to implement. Or possible to implement, it just takes forever. Now let's look at another type of modulation. Here, we've taken the same modulating signal and replaced the zeros with -1s. That is, we're multiplying the carrier wave by -1. This has the effect of producing a phase shift by 180 degrees while leaving the amplitude the same. Or at least we would be leaving the amplitude the same if it weren't for the pulse shaping. So if you look, you can see the zero crossings here. And you can see that if you count on here, there should be a bump here, but there isn't because we've had the phase reversal at this point. The square wave here is the original digital. This line is the pulse-shaped waveform, and the blue is, of course, the carrier wave. Well, the RF signal. It's the carrier wave that's been multiplied by the modulation. So, however, in doing this, in changing to phase shifting, we've introduced an ambiguity. When the receiver starts receiving the signal, it doesn't have any reference phase, and so a phase transition could be from 0 to 1, or it could be from 1 to 0. This isn't a serious problem because we need more synchronization information anyway to make sense of the bits. You know, a known sequence at the beginning of the packet can resolve this ambiguity, or you can use a differential encoding where, you know, a phase transition stands for 1 and no transition stands for, or vice versa. Or lots of ways to do this. Yeah, one of the things you will see here is the thing about digital modulations is there's lots of ways to do them. There's far harder than if you're doing like just FM audio or something. Right. Before I discuss more complex modulations, let's look at what it takes to demodulate this signal. If nothing else, so that this fairly messy picture gets cleaner. What we have in this case is a carrier wave the first step is to perform a frequency shift to return the signal to baseband, which, for those that weren't here the first time around, is just a matter of multiplying it by another complex sine wave, which has the effect of just giving it a twist, and we give it a twist all the way back. Except not exactly, because, of course, no two running oscillators are going to be at exactly the same frequency, so this won't give perfect results, so we need to give a final correction. There are a number of algorithms which can be used for this purpose, depending on the particular modulation in use. In any case, we have now a true baseband signal with no twist. Baseband meaning we've returned the frequency to 0. You can see it doesn't have any twist left to it, which means that this is, in fact, a real number valued signal. Anyway, the next problem is that we need to recover the bits. We need to slice this signal up along the time axis. Remember, this is a digital signal, so we already have it sliced up in a sense, but we have far too many samples. We want instead to have exactly one sample per bit. To do this, we need to take those samples in a way which is synchronized with the digital clock which generated the bits in the first place at the transmitter. This is necessary to ensure that we don't read samples halfway between two bits and read nonsense. Again, there are various algorithms for synchronization. I'm going to skip the details for that. We definitely do not have the time. But let's just assume we've in fact done that, and we have the original still represented as plus and minus 1. I've also conveniently assumed that we've recovered the exact original phase, and so this is all lined up on the y-axis. Now let's take the end-on view. Here, we stop being able to see the actual data because we just compressed the time axis to nothing, and we instead see just all the possible phases in the signal, all the possible positions in the IQ space of the signal. This is known as a constellation diagram and is a very useful representation of digital signals, or rather digital modulations, I should say. I told you this was first draft. There's lots of empty space in this diagram. In fact, we're only using one dimension. There are two available. Let's do that. So now there are 4 dots rather than 2. The digital signal has 4 possible values rather than 2. Since there are more than 2, each dot represents more than a single bit. So we call these symbols. It takes 2 bits to identify one of 4 things, so there are 2 bits per symbol in this case. Now, remember, this is the complex plane, so an angle from the origin here corresponds to phase, so we can see that there is 90 degrees of phase separation between any 2 symbols. This case, with 4 symbols, is called quadrature phase shift keying, or QPSK. In general, you can have PSK with any number of symbols, but as the number of symbols increases, the decreasing separation means that a better signal-to-noise ratio is required to receive the symbols without error. If there were noise in this signal, then you would see it as the single points becoming fuzzy clouds of samples. A decoding error occurs when the noise pushes one of the samples to being closer to a different symbol than the correct symbol. In fact, if we can see something like what it might look like. Suppose we put in an entire grid of points. Ignoring what it means for the moment, we can see that the diagram implies this ought to work just as well. It's got 16 symbols. They're each therefore carrying 4 bits. This general case is called quadrature amplitude modulation because unlike the we just saw, the points don't lie on a circle, or you can see that there's this circle and this circle and this circle, but that's not useful. But the points don't lie on a circle, and therefore the amplitude of the signal as well as its phase is being changed. QAM has very good spectral efficiency, data rate per bandwidth used, but because it's using all of the degrees of freedom available in the signal. However, it does require good linearity in both the transmitter and receiver, since the amplitude distinctions are critical. QAM is commonly used in high bandwidth applications, for example, in digital cable TV and internet service, where constellations with up to 256 symbols are used. I probably said at least one thing that's wrong, by the way. And Jay, I expect this audience can spot it. So now that's all the material I have for the moment, unfortunately. One thing I haven't covered is frequency shift keying, modulation, which is very common in amateur radio applications. It doesn't fit into this model, so that'll be another topic for a future presentation. But it's basically frequency modulation with discrete levels instead of an audio signal. That's, as I said, that's all I've got for the moment. We'll have to revisit this later.
Just to add to that, DOCSIS 3.1 has 4,000 point constants.
Okay, I got all my information from Wikipedia, sorry. Yeah, I mean, all of those incidental facts, I mean. Yeah, so as I said, that's it. I'm currently planning that if I do this again, each topic will be sample rates in digital signal processing and how to convert between them and why you want to, and the efficiency issues with doing that. That's what I'm currently tentatively planning to, but I certainly haven't written that. And if I've got another minute more, I'd like to plug something. Namely, presumably most of you here are programmers. You've probably used stackoverflow.com, or at least heard of it, or just place, or one of the above. It's of course part of a whole network of sites, and some of them are very relevant to the topics we discuss here. There is a Stack Exchange site dedicated to the topic of digital signal processing. There is one dedicated to the topic of electrical engineering, which is the other half of all of this, and there is one dedicated to the topic of amateur radio. That one interest in. So if you are interested in the subject and you like the Stack Exchange format of actual questions and answers and not rambling discussions, then I encourage you to check out ham.stackexchange.com and help grow our site. Thank you. Oh, wait, I forgot. Okay, let's see. Come on. Wake up. Oh, there you go. Okay, now you can applaud.
Thank you very much, Kevin. All right, so next up, Matt would like to do your thing. And, the mic off for you.
Oops. Oh, yes.
Will it reach? Okay. While that gets set up, I'll just do a brief introduction. I'll just do a brief introduction while Matt gets set up. Actually, Matt Edis doesn't need an introduction, but we'll give him one anyway, because otherwise he'll feel left out. So Matt is a core contributor to the GNU Radio project and is the creator of the Universal Software Radio Peripheral, USRP. In 2004, Matt founded Edis Research to develop, support, and commercialize the USRP family of devices. Edis Research was acquired by National Instruments in 2010, and Matt continued as president. In the past, he has designed Bluetooth chips, GPS systems, high-performance microprocessors. Before that, Matt received his BSEE and BSCS degrees from Washington University and an MSECE degree from Carnegie Mellon. And I'll turn it over to Matt now. How does it? Okay, ball, which button? This?
Oh, it's off.
Okay. Okay. Okay, so I'm going to be talking about synchronization, and in particular, synchronization for MIMO systems. Now, in the previous talk, there was a mention of synchronization as well, but that was more of a, how do I synchronize timing signal on my receiver so that I can recover carrier frequency and phase and timing and that sort of thing. Actually, not the synchronization I'm going to be talking about. That's very important. But what I'm going to be talking about is how you synchronize multiple radios together to make them into a larger MIMO-capable or phased array-capable system. And so this is hardware that would happen all at the transmit side or all at the receive side, and then you still need some sort of synchronization to the incoming signal on the receiver so that you can recover the signal that was sent from the other side. So that being said, I have a bunch of areas that I'm going to hopefully get to, not all necessarily in order, but this is the basic outline. I'm going to skip around a lot. I have just a small number of slides with some diagrams and things, and so I'll be jumping back and forth. But at any point, if I'm unclear or I'm skipping over something, or if you remember I missed something from this list, just let me know so that we can so that I get to that. Or if there's any specific questions you have, just jump in. I just intend this to be pretty free form. But I'm going to start with clocks and time and how we synchronize multiple usurps, and in the larger sense, how most people synchronize their radios. And we'll get into PLLs and phase noise, GPS for synchronization, and then into the clock architectures of common radios and how we build them, and then what's required for phased array MIMO and geographically distributed MIMO systems, and then some specifics on how we do all of those, and the performance characteristics that are necessary to make good systems. So why is this important? This is a picture showing a 100 by 100 antenna MIMO array. So that means 100 simultaneous transmissions and 100 simultaneous receptions for a massive beamforming array. And this happens to be at the University of Lund in Sweden. And so these are 50 USERP X310s, and each X310 has 2 antennas. So this has 100 antennas, and they all transmit a coordinated signal. And in this case, they do that so that they can beamform a very strong signal to a single antenna user device that's walking around. And vice versa on receive, when this user device transmits a very weak signal from one antenna, the 100 antennas are used to receive at the base station. So this is used in research for what is being called 5G, which is the next thing after LTE for wireless communications. And so massive MIMO is one of the possible technologies that will go into that, and this group is researching that using USRPs. But the important thing is, so we've got 100 antennas, 100 data streams coming in and out. How do we make that into something useful? How do we form a beam in the right direction or to the right user? And the key component to that is synchronizing everything. And that's in phase, in frequency, in time, and there's multiple sub aspects of that. And so this is the goal, and because we have all of the pieces right in our synchronization architecture, we're able to do systems like this. So this is sort of a generic SDR block diagram, and but with particular emphasis on the clocking. So let's see if this works. So first, the signal chain part, you would start with your application that generates some data, and you do whatever processing on it in, say, in a host computer. And then that data somehow gets to a DAC, and the DAC forms an analog signal from that, and in this case, at quadrature baseband. So these are all I and Q, most of the arrows along the main line here. But just for simplicity's sake, I just showed it as one arrow. So you have your DAC, you have your baseband signal that gets filtered, and then we have a frequency mixer that mixes it up to the channel of interest, and then an amplification, possibly filtering, and then it goes to the antenna. Now, not all radios follow this exact diagram, but you can effectively model all radios like this. Let's say you had a super heterodyne, you might have 2 mixers. It doesn't really matter, you can just model the 2 mixers in this system as one mixer of the frequency you're mixing with is either the sum or the difference of the other 2. So this is effectively covers all architectures for a radio. So now you have your baseband signal, you want to mix it to your RF. So let's say that RF is at 2.4 gigahertz. So you would have to mix it with a 2.4 gigahertz signal. And so you have to generate that in your local oscillator. And this little structure here, this is a PLL, is simplified drawing of a PLL. Is everybody familiar with PLLs? Okay, good. So this PLL, in this case, is generating your local oscillator. So if you're transmitting on 2.4 gigahertz, this guy's at 2.4, and here you have signals that are complex, and they're from negative some, let's say negative 20 megahertz to positive 20 megahertz. You have a 40 megahertz wide signal. So that's the local oscillator. The next oscillator that's important in the system is the oscillator that clocks the DAC. And so we call that the sample rate clock. So we have local oscillator and then the sample rate clock. And in USERPs, the sample rate clock is also the master clock in terms of everything that's on board. So the local oscillator is locked to the sample rate clock. And then the sample rate clock is itself locked to an external reference, the master reference. Now, if you don't connect to an external reference, then let's say you have a USERP N210 or an X300, it has an onboard TCXO that will free run. So you would have a 10 megahertz free running oscillator here. Then in, let's say, USERP N200 series, you would have your sample rate clock is generated at 100 megahertz. So this PLL locks to this oscillator at a factor of 10, so 1 is 10 megahertz, then you go up to 100, and then you have a PLL that would then generate your 2.4 gigahertz here. So that's the basic structure. Now, if you did have an external reference, let's say it came from GPS or some house frequency standard with a 10 megahertz cable, then that would come in here. And so then you would be locking the onboard TCXO that's 10 megahertz to the external 10 megahertz. And so that's when, if you were to use the external 10 megahertz input on your USERP. If you use a GPS disciplined oscillator, it is pulse per second information that it gets off of, or an estimate of the time that it gets off of GPS to lock its own 10 megahertz reference. So in any system like this, there's many, many steps of locking to progressively higher and higher frequencies. And actually, you could even argue that back here, on the other end of the GPS constellation, there's the GPS system is then locked to a hydrogen maser, which is locked to NIST standard time, and it goes all the way back to narrower and narrower loop bandwidths, tighter and tighter precision, and then you get looser precision as you go out because you're getting to higher and higher frequencies. So that's the basic structure, and there's some variations on it. For example, not all radios would lock their local oscillator directly to the master clock. They might lock it just to the master reference over here. It doesn't really matter in the grand scheme of things, but this is the way we do it. There's an advantage this way, but you don't necessarily have to do that. So this is a sort of a general clocking diagram for a radio. And older radios, let's say, well, before the software radio era and when PLLs were more expensive, you might actually have a crystal generating with multipliers and all sorts of other stuff that might not even be locked to the same master reference. So not all older radios lock to their own internal reference, and they might have multiple oscillators that sort of drift independently. But modern radios all do this sort of thing. Does this diagram make sense to everybody? Okay, good. So that's the general architecture. And just to illustrate sort of why we need this, this multiple stages of clocking, and locking each one to a progressively lower and lower clock. When, let's say our GPS gives us 1 pulse per second, well, why don't I lock my 2.4 gigahertz thing directly to those pulses per second, for example?
And the reason is for phase noise. So this is a plot of phase noise. Has everybody seen a phase noise plot before? No? Okay. So the concept behind phase noise is any oscillator is not perfect, and it's going to have some noise. And that in an oscillator, you don't tend not to care about the amplitude noise because you're just using it as a frequency and a phase. And so we just look at the phase noise, and you ignore the amplitude noise. So the phase noise is a jitter back and forth. So if something's supposed to be going around like this, and every now and then it sort of bounces a little bit, that results in phase noise. Now the phase noise it tends to have this shape, if you've designed your system properly, where phase noise that's very slow, it can be quite strong, but then the faster the phase noise, the further it is, the bigger the deviation from your frequency, the less power there is in it. So this is a log scale. So at 1 hertz, you might have a significant amount. This is all in dBc, so this is relative to your power. So you might have 1/10,000th of the power of your signal is essentially devoted to oscillation at within 1 hertz off. But then you might have 1/100000th that's 1 kilohertz off, and so basically the noise. If you look at this on a spectrum analyzer where you don't have this log shape, you basically see just something curving like that. And so if you put a clean LO into a spectrum analyzer, that's what you'll see. If you put a noisy one in, you'll see more. So when you lock, so this is the basic shape of phase noise of all oscillators. Yes.
Can you get rid of the microphone?
Yeah, sure.
Sounds like
Here,
you're talking
well,
over an old radio link.
So why don't I just go
Can you
without
put it to the side? I think it's because you're with the receivers there.
You just record speakers here so that everybody can hear it directly, and just the people online will hear it through the microphone. Does that make sense? Okay. Yeah. So in any case, you've got this phase noise, and the natural shape of an oscillator is, and I'm going to draw this here. The natural shape of any oscillator will be like this, and but oscillators will drift. So, for example, in this picture, there's an oscillator here that is a voltage-controlled oscillator in our synthesizer chip that we use on our devices. And it will have this noise shape like this, but it'll drift all over the place. So the phase locking is what keeps it at the right frequency. And to use the lower noise, lower frequency reference to clean up that oscillation. Noise like that. And as you go progressively lower in frequency, you see essentially the same shape. Yes?
Use a different marker. That one's not coming out.
Okay. Bigger problem, I suppose, no matter what color I use. So in any case, the model is you progressively lock. So you take a pulse per second that you get off of GPS, and you use that to lock a 10 megahertz reference. But you have to have that pulse per second is very noisy, so you have to average it over a very long time. That's a narrow loop band within your PLL. And now, when you do that, this uses a nice quality voltage VCXO that gives you a 10 megahertz reference here. And then you multiply it up in a USERP N200, you multiply it up to 100 megahertz using another PLL that locks, that creates a clean 100 megahertz oscillator, or 200 in the case of the X300 device. And then you progressively multiply that up to your LO. So those are all the oscillators in the system. Now, what happens if we have multiple devices? And so that we wish to synchronize. So here, this is an example. If you do the B200 and the E310, which have an integrated RF chip, so a lot of this all happens in one chip here. And so, but antenna system in the B210. And so antennas share all of the references, right? So the sample clock is shared because it's within the same device, and the local oscillator is shared because it's in the same device. That has an advantage in that you now have a well-defined phase relationship between these two paths. And that allows you to do things that are known as phased arrays. So, so I'm going to jump around a bit here. Yeah, I'm going to take a step back. The different sorts of requirements for multiple antenna systems. In the larger sense, you can call all these multiple antenna systems MIMO. And so in the general sense, they're all MIMO, meaning multiple input, multiple output. But there's also a more specific definition of MIMO where MIMO OFDM type communications has certain requirements where in particular they care about the sample times being locked and coincident, but the absolute phase on the RF is not as important. A phased array is a multiple antenna device where the absolute phase on every antenna is important because you need to direct a beam. So to draw it, I'll draw it. Direction. On the frequency. Right, and so, and that signal gets here, it'll add in phase and coherently. But in order to do that, you have to have a very well-defined phase between each antenna. So a phased array system is a more strict case of the general MIMO system, where you not only have to have time synchrony, but you have to have known phases between the ports. I'll get into geographically distributed MIMO systems afterwards, but those are the basic terms. So again, MIMO requires everybody's sample clock to be essentially the same time. Phased array requires both that and everyone's phase to be a known difference between each port. So we go back to the B210, and if you were to use this for a MIMO system, you don't care about the relative phases between these two, but they'll be aligned. So it's more than you would need. But you also have the timing aligned between the two. And so the B210 is suitable for both MIMO and phased array with its two antennas. And the reason is because you just share the reference. So of course it matches. Now, there will be errors in any system like this. So these, these are real wires with real components along them. So there's some phase error between them that will change with temperature, and different devices will have a slightly different phase. But in all of these systems, you can calibrate that out. And in particular, in this one, the calibration is pretty much just a function of device and temperature. So you can sort of do it once for each device, and you just apply the calibrations when the temperature changes. So in a system like this, and I've just drawn transmit, I haven't drawn the receive, it's all reversed for receive. You can put if you have the DSPs generate the same signal that goes into the DACs, and the DACs send it at the same time through here, they get the same LO, they're mixed up, and they should come out completely in phase with each other. In practice, there's analog errors in all of these, and so the amplifiers will have slightly different frequency errors, and the filters in particular will have huge frequency errors. So anytime you have a filter being a high Q device, will dominate all of the phase errors between paths. But because these are all fixed components, you can just calibrate them over temperature, and that's it, and you can make your phased array. So you might, in normal situations, this might be 5 degrees ahead of this, so you just apply digitally your 5 degrees back there, and it comes out phase aligned. Excuse me. So that's a simple phased array system based on a B200. Now this is an X300, which also is a 2x2 MIMO device, but instead of having that single RF chip that does 2 full RF chains, it has 2 separate daughter boards. And the daughter boards have the same basic components in them, but each have separate local oscillators. So now it becomes a little bit harder if you care about phased array capability. Because in a phased array, you need to have a well-defined phase between these 2 local oscillators. If you don't care about phased arrays, if you're just doing MIMO, you don't care about the relative phase between them, as long as it stays constant while you're operating. right? Every time you tune, it might be different, but as long as it doesn't change during a signal, it's fine. And so because they're both locked to the same reference with the same parameters, they might come up with a 37-degree difference, but it'll stay a constant 37-degree difference. So this is, as it is suitable easily for MIMO, but it's a little more difficult for phased arrays because you would need to calibrate that phase difference. And so you would need to design your PLLs in such a way that they have a known phase error every time they tune. And so on our SBX and our UBX products, we have that capability. And so you can effectively get a phased array easily. And again, you still need to calibrate, but you just calibrate once. On our WBX and our CBX, we don't have that alignment capability. And so you either can't do a phased array or you need to calibrate every time you tune. And every time you tune might be okay in some applications, but in others, it's a requirement that makes it a non-starter. So again, are people following me? Am I being clear? Good. Okay. So yeah. So this is all one motherboard on the X300, and then two separate daughter boards with separate local oscillators. Now that's two antennas on your X300, but I showed you a 100 antenna version, and so let's say you expand to multiple motherboards, each shown in blue here, and each motherboard then has its two daughter boards, and within the motherboard, again, they share the sample clock and they generate independent LOs that are of course locked to each other. But then between motherboards, they each generate their own sample clock, right? Because they have separate local oscillators. What is the terminology I'm using? Separate master clocks, right? So they each have a separate master clock, but in this case, they're both tied to a common master reference, whether this is a GPSDO or just a house 10 megahertz reference that you have running around. So now you have frequency error between these two guys. You have phase error between these two guys, and which you can calibrate. And then you could have phase error between these two guys, because even though they're both 100 megahertz, they need to be locked to the same reference, but they'll have slightly differing errors. And so where was I going with that? Yeah, so in any case, yeah, so you have two separate references. So they each take a 10 megahertz in and they generate their own megahertz, which are used internally. And of course, this would, you could have hundreds of units like this and synchronize them all the same way. And this 10 megahertz distribution system, in the case of the diagram I showed, is our octo clock. So the purpose of the octo clock is it distributes 10 megahertz and PPS signals to 8 systems. In the 100 antenna system, it has 50 usurps, so we have 8 octo clocks, each outputting 8 references, and then those 8 octo clocks are each then driven by 1. So we have actually a tree of 8 times as many outputs at each level. You get 64 phase coherent 10 megahertz and PPS signals, and a hell of a lot of SMA cables to connect all this. So, right, and in this picture, what you don't see is, they've hooked up the PCI Express cables, but they have not yet hooked up all the synchronization and RF cables. Once they do that, you really can't see the traces of the boxes because they're covered with SMA cables. There's a lot of them in order to maintain this synchronization. And so this is actually a good time to talk about PPS. So the 10 megahertz is obviously gives us a time reference, a time and a frequency reference. So why do we also need PPS? Especially when the 10 megahertz has been generated from PPS. So aren't they redundant? And the answer is, to a first order, yes, they are redundant, but there's some practical reasons why you still need the 1 megahertz, the 1 PPS. So 1 PPS stands for 1 pulse per second. Now, and the reason for this is that even though you can make sure that the DACs are both outputting at exactly the same time because they have the same, in this case, 200 megasample per second clock here, you have to make sure that the DSP, that each DSP is providing samples to the DACs at the same time. So if one DAC, you have 2 time streams, you have to align those time streams. And because the time streams are coming to the device over Ethernet or PCI Express, it's a completely asynchronous interface. So you have to make sure that you get them there at the same time. Now, to the device, at this point, every 100 megasample, or sorry, every 200 megasample per second clock, so every 5 nanoseconds, looks like every other 5 nanosecond clock. You need some way to differentiate between one clock and the next clock so that every device in the chain agrees that sample number 1 starts at this 5 nanosecond clock. And so how do you differentiate? If you just have a 10 megahertz or a 100 megahertz or 200 megahertz signal, there's no way to differentiate between all of the pulses. And the way you differentiate is by providing a slower signal, which marks one of those as this is the epoch, or this is everybody start counting now. And so you use one pulse. There's nothing magical about 1 pulse per second. It's just that it's slow enough that everybody can agree if we all heard a 1 pulse talking about the same one. If we all hear, you could use a 200 megasample per second clock for that, but then it's very hard to differentiate. We won't all agree on which one is the matching one. So with 1 pulse per second, it's easier because it's 1 pulse per second is longer than every latency in your system, hopefully, and it works. You could do fine with a 100 hertz or kilohertz even, but much faster than that. You might run into situations where there's some hiccup on one device or the other, and they don't agree on the count of the 200 megasample per second clocks. So the pulse per second is to disambiguate between the higher frequency clocks and mark one of them. Does that make sense?
Yes. I'm unable to see the pointer.
Okay.
So if there's something important, could you point?
Okay, good. Yeah, I actually, probably people here can't really see it well either. So I won't use it anymore. I'll just point. So that's the purpose of pulse per second. The pulse per second is also used internally in the GPSDO to generate your 10 megahertz. The pulse per second is pretty noisy, but you don't care about that because as long as it's not noisy enough that it moves more than one 10 megahertz cycle away, it's okay. Or more than one 100 megahertz cycle away. As long as it occurs every, exactly once per second, exactly once every 10 million or 200 million sample clocks, then it's fine. And so it can be noisy. It's a digital signal. We just passed it through the FPGA because jitter on that is not critical. Jitter on the 10 megahertz, the 100 megahertz, the 200 megahertz, that is critical. You never pass that through the FPGA and then use it in an analog place. Let's see. I'll go back to my list of topics and make sure we got it. So we got 10 megahertz of PPS clocks and time, PLLs and phase noise we covered. We did GPS a bit. So now, okay, so let's go back to this case. So on the B200, right, we have a shared local oscillator between the two chains. It's guaranteed, unambiguous, everybody gets the right clock. X300, on each daughter board, you have a separate local oscillator. How do we guarantee that these two are lined up? And so the first thing is that they're given the same reference. So they're both clocked off of the same reference. And if they both have the same settings, they will both generate the exact same off of that. That's easy. That's trivial. That's just sort of by construction. Then the question is, well, now how do we phase align them when we need that? Meaning, not just that we both have 2.401 gigahertz here, but but that the 2.401 gigahertz is in the same phase on both devices. And there's a couple of different ways to do that. One is you have to sort of look at the internal architecture of a PLL. So this is a simple one. And the PLL is really composed of, I drew just a very simple picture where we have phase frequency detector, loop filter, and VCO. But in an actual one, it's more complicated. You have dividers. So for example, if you send in 10 megahertz here, and you have a divider of 2, you would have 5 megahertz here. That means you're automatically going to have 5 megahertz here if the clock is locked. And if this is a divide by 100, then that would mean this is 500 megahertz, and that means 500 megahertz is coming out here. Megahertz is stole analog devices picture. So the PLL is used to both lock the phase of two devices, but also change their frequency. So if your reference is 10, we've generated 500 here. And now, in the case where you start with a reference and your output of x, and your output is some integer number times x, then you will typically have the phases matching, right? There's no ambiguity. But if you start with 10 megahertz, you divide down,
and then you multiply up by a factor that does not include that same divider, you'll have a phase ambiguity out here. And it's sort of a subtle concept, but if you think about when you do a clock divider, let's say you're dividing by 2, there's 2 possible phases of that output. So if you have 2 separate dividers, even if they're dividing the same thing, the 2 separate dividers could be different. If it's a divide by 2, they could be the same or 180 degrees out of phase. If it's a divide by 10,000, there's 10,000 different choices of relative phase. And so in the early daughter boards, like the RFX series, if anybody remembers RFX 900, RFX 1800, those in order to get this phase alignment was you were forced to use a multiple of the reference clock. And by you having a multiple of the reference clock, you could guarantee this phase alignment. But that's really inconvenient in a lot of cases. It makes it so that you can't get fine precision in your local oscillator frequency. And so modern PLLs are much more complicated, and they do things like fractional n. So now we can multiply not even just by integers, but by fractions. And it becomes much harder to guarantee that if there's 2 of these, even if they get the same reference in, that their outputs will be in phase. And so what in this case, what we rely on is some functionality built into the PLL to where we let it lock, and then we give it a kick that says align yourself now. And if we kick both of them at the same time, and you do it exactly right, it will generate phase-aligned outputs. Only certain PLLs are capable of doing this. So, for example, the PLL that we use on the SBX daughter board and on the UBX daughter board is capable of doing this. The one we use on CBX is not. It's an older device. So CBX is not really that suitable for a phased array, whereas SBX and UBX are. And WBX also uses one that's phase alignable, but it has a mixer which has its own divide by 2 in it. Because it's outside the loop, there's a 180-degree phase ambiguity. So the WBX can be used for phase arrays, but you'll always have this 180-degree ambiguity that you would have to calibrate out. With the CBX, you'd have a 2 to the 16th ambiguity. It's not really, it's too much to figure out. But the 180, you can easily tell which it is. But the ideal for phased arrays are SBX and UBX. Yes?
What kind of signal do you use to kick it off, to align that?
So actually what you do is, do they show it here? They don't really show it. But essentially what you're doing is you're resetting all of the dividers in front of the phase detector. And because you have these dividers here that could be different on the 2 devices. And so it's just a digital signal, but it has to at a precise time relationship to the master clock. But if both devices have that, then this whole chain, which has dividers and in this case a lot of other junk in it, it gets to here. Then you know that this reference point in both devices matches. And if one input matches to the phase detector, the other input matches. So that's one thing. That will guarantee that the second input to the phase detector matches. The critical piece of it is this is sort of more getting into the weeds, but that signal that's going to the phase detector is what matches. But if you follow it by dividers going to your output signal, those dividers have their own ambiguity, so they could be 180 off for each one. So what you end up doing is you have to form the loop. That's why it has this mux. So instead of taking the VCO before the divider, you take it after the divider. So it takes a lot of work. There's a lot of magic that we just so you don't have to deal with it. But that allows you to guarantee this phase alignment. Now, again, you still have analog component variations that you have to calibrate out, but any phased array system, even if it shares every oscillator without doing this kind of thing, still needs the calibration. So yeah, so that's a more complex PLL, and that's what you'll see in our devices for the local oscillator side. Balance, how long am I on time? Okay. So let's see. So now I'll talk a little bit about errors that you might see in calibration. So where did these come from? So and we actually had a customer doing a phased array just last week, I think it was, that sort of was the motivation for me doing this talk. But basically what he was doing is exactly this system here. He had SPX daughter boards on all these, so it was capable of phase alignment. And he was then generating a signal from a SIGGEN, splitting it to all four. And in GRC, he was expecting all four signals to be, from the four channels, to have a definite phase relationship with each other and not to change. And so was that these two had a very good phase relationship with each other, and those two had a very good phase relationship with each other, but the two pairs had more noise between them, and they were jittering back and forth. And it turned out what was happening was that because these in here matched, it meant this part was good and their mutual phase noise. So I'm going to take a step back here and pop the stack a bit. So because we're independently generating these, they each have their own phase noise. And so they will have mutual phase noise. So if you're taking a relative angle between this signal, you not only have this phase, but this one has phase noise, and those are uncorrelated. And so their mutual phase noise is essentially an RSS sum of their individual phase noises. Now, if you do this other architecture like here, then they have no mutual phase noise. No matter how much phase noise there is here, these guys will have no mutual phase noise because the phase noise will match on both paths. But if you generate separate oscillators, then they'll have mutual phase noise. And so the way to minimize that is to minimize each one's individual phase noise. And so that's what we've done. And so he found that in this case, he had very good mutual phase noise between these two. It was very low. But across the pairs, they had higher mutual phase noise. It had about 15, 2.4 gigahertz or something. And it turned out that was because they were getting higher phase noise. They were getting mutual phase noise at their, I can't reach, sorry, at this point and this point from their internal master clocks. And so we were able to change the parameters of the PLL to lock these closer together so that now he was able to get the same phase noise across all four and have a usable phased array system. Now, so since everybody's locked into the same 10 megahertz reference, anything that happened, but they split after that point, anything that happens differently on one channel versus the other will affect the systems differently. And in this particular case, what was happening is that air was blowing on one of the oscillators, this oscillator in each, because it's in the device. Air blew on one, and it blows on the other, but air is turbulent, it's random. And so a slight different temperature on one was causing a very small jitter versus the other one. And he was seeing 10 degrees at 2.4, works out to 11 picoseconds. So we were getting about 10 or 11 picoseconds noise between this guy and this guy. And in order to improve that, there are two options. One, you can keep the air from blowing on it, which is a good idea. But what we did was we actually just changed some parameters in this PLL to make it more immune to phase noise on its input, and or to lock better. And so that was we were able to improve it like that. But it gives you an idea when you're talking about 6 gigahertz, 5 gigahertz, signals at these frequencies. 15 degrees of phase sounds like a lot, but in a really tiny number. And so you have to be very, very careful with all the components in the chain. And so just even differential airflow across them can make a big difference. So in any case, we got it down to 1 degree of phase error between all of them continuously just by changing some parameters. Okay, so now we talked about this is sort of our massive MIMO setup where everybody's close enough to each other that they can share a 10 megahertz reference. What if you want to set up across miles or hundreds of miles away and still have a MIMO system? Can you do that if you can't afford to string 100 miles of SMA cable to send your 10 megahertz and your PPS? How do you? What we do, it's what we call distributed sync or geographically distributed MIMO, where instead of sharing this oscillator, this 10 megahertz house standard effectively, we have two separate ones, and they're each generated locally to their setup. Now, we've had a number of people do this in real practical systems, and as long as you understand the performance characteristics of that, you can make it work. One of the things to understand though is that GPS, while it's incredible, you're still going to have sort of 50 nanosecond differences. So a phased array like this is not practical because 50 nanoseconds would translate to thousands of degrees of phase difference between the devices. So you can't do a phased array. But you can do a MIMO system where everybody's time is synchronized within 50 nanoseconds. And just, you have different phases. But a general MIMO OFDM system, again, we know doesn't care about absolute RF phase as long as the timing is consistent. And in particular, the timing needs to be consistent to a less than one symbol period of the MIMO, or really less than the cyclic prefix time of the MIMO, of the OFDM. So in wider systems, let's say we're doing 802.11, 802.11 has an 8 nanosecond cyclic prefix, I believe it is. So you wouldn't be able to do that with GPS. But LTE has a much longer cyclic prefix, and so the geographic, the differences between the two GPSs would be covered by differences in arrival time of the signal. And so essentially the key takeaway from that is you don't have to worry about time differences that are smaller than your relative propagation errors tend to be, or your multipath, right? So if the system is designed to handle multipath of 1 microsecond, then you don't really have to synchronize to better than 1 microsecond because your synchronization error just looks like a path length difference of a microsecond. Let me draw that. So let's. I'm going to draw it over here. Sorry to those on the online. So if you have two antennas, right, at two very different locations, and if only synchronized to 50 nanoseconds and not perfect, in the picoseconds, it doesn't really matter if you're talking about a system where the path length difference from them would be of a bigger order of magnitude. So if this is, a microsecond difference than this, if this is T1 and this is T1 plus a microsecond, then it doesn't matter that you're off by 50 nanoseconds as long as you can take care of it in your DMOD. But in 802.11, you couldn't do that. It has too short of a symbol period. So let's see. I think that's all I got. I think everything in my list. Does anybody have any questions? Otherwise, I will pass it on to Martin. Oops.
Is there any advantage to having such a diverse antenna spread, like essentially?
Okay, so in some systems, we see that there's value in that. So one example is if you're doing let's say a spectrum monitoring system where you wish to where you wish to determine where somebody transmitted. Let's say you want to look for the bad guy in some area, and you set up on all the light posts in a region and listen for a signal, and then everybody who hears it then reports back to the central location, and you can do a time difference, right? So you can do a time difference of arrival that way. And so if you, let's say you have this network of a whole bunch of stations, and you know that that it got to this guy first, this guy second, this guy third, and it's probably closer to here. You can do a localization of it. That's called TDOA, time difference of arrival. There are also angle of arrival systems. Angle of arrival, you couldn't do with that because there's too much error. You can only do angle of arrival with a true phased array system where the antennas are local and share the master reference. So angle of arrival, and very often these are used in conjunction. So you might have multiple antennas in each one, and they can do angles from each one, and if this guy says it's this angle, and this guy says there, you know where it is. So angle of arrival can only be done with a true phased array capable device, whereas TDOA can be done with much less precision.
And typically, like if you want to really do a DMOD, I guess you need to lock into the receiver. Right. Synchronize clocks as well as do some channel estimation and things like that.
Right. So if you look at that massive MIMO system I showed, the antenna that they put on there is actually what I would call a phased array antenna, right? Because they're uniformly spaced, and this looks like they're trying to do sort of a direction finding like that. The reality is what they're doing is more interesting than that. Rather than picking a specific direction, because there's so much multipath, it's a much more complicated than that. And you can do systems like this with just sort of randomly spaced arrays, where instead of having to have a precisely defined location for each antenna, you could just sort of place them randomly. You don't even have to have match length, coax lines. You can have all sorts of weird lengths, because all of those lengths, all those differences in length, when translated into time, those time differences are smaller than the multipath would be. Right? So if the multipath might be 50 nanoseconds worth of multipath, as long as your time deltas are smaller than that, you're okay. And you can coherently add them together and demod the signal. And so we have had people do a geographically distributed system where it then does coherent addition, but it has to be a much narrower band, meaning much slower symbols. So, for example, there's a company based up in San Francisco that is now doing this sort of distributed MIMO technology or at higher frequencies, but at the time they were doing it on HF radios, like 10 megahertz. They had a signal that was about 3 kilohertz wide, so 30 milliseconds, the 300 microseconds. So as long as everything that they had was spaced at significantly less than 300 microseconds, then they didn't have to get any more precise to it. Right? They can calibrate out the errors. So they had just systems placed, in their case, all over Austin, Texas, and wherever they could find a farm or somebody would let them set up. And they were able to do a coherent demodulation on that because they were doing slow signals. So as long as your accuracy is better than the dispersion you'd expect from multipath and from propagation delays, then you can do the system. Okay. Yes.
Multiple radios.
Yes.
The UHD driver, does it put all the packets together so you get one coherent?
Yes.
Okay.
Yeah. So if you use the multi-UHD, and multi-user sync, it will take whatever stack of radios you have, and in GRC it'll give you one big block of, a bunch of ports on it, and one for each antenna, and will automatically align those for you.
Okay.
And so you'll get a stream for each one, but if you take the first sample off of each stream, that's the one that's coincident in time.
Get those O's. Does
Right.
that cause any problems, or are you just like zero fill?
So we don't drop samples per se, at least in the Gen 3 devices. You will get an overflow. In an N200, you could drop samples, and you would be notified of that, and you'd have to stop, restart, and they would be aligned again. In the newer devices, it doesn't drop because of an overflow. It holds it back, so you always get time-aligned stuff, and anytime you couldn't keep up, it would shut everybody down at the same time and restart and you would have to manually, in the program, manually restart everybody coming in again so that it maintains the alignment. So it won't give you misaligned. Martin, correct me if I'm wrong. No, whatever happens, it won't give you misaligned. But if something happened that would cause a misalignment, it stops and you restart. So it never gives you bad data. That's the critical thing. So yeah, it's a lot. The vast majority of the complexity of this is all handled under the hood, so you don't have to worry about it. You just need to know how to call it, right? You can't just say, you couldn't independently say to the two usurps, okay, start sending me samples, because you wouldn't know when they're aligned. You have to tell them, hey, both of you start sending at time X, and they will both start sending at time X, and then everything's automatically aligned. Yes?
So with the GPS, what's the cause of the 15 nanoseconds?
So that's just natural errors in
Is it from
GPS.
propagation?
Well, so GPS just naturally has a certain amount of error to it.
Okay.
Now, if you take one GPS antenna, splitter, and into two devices, there will be a very tiny amount of error between the two. But if you put two antennas next to each other, they will have more error. It'll be on the order of 25 nanoseconds RMS. As you move those antennas further apart, they have different, even views of the sky, and they will have more error. So if they're 100 miles apart, they'll have a little more error, and 1,000 miles it's worse. And then once they have no common view of the sky, then they have more significant errors. And so typically these aren't like one thing on one side of the Earth, one on the other. It's more like, within 100 miles, and you get the best results then. So GPS isn't perfect. It's a very weak signal coming in, and you're locking to it, and it depends on the quality of the oscillator and how good the loop is. And so we use a module that's in the South Bay called Jackson Labs, and they specialize in this, and they produce. They're able to get 25 nanoseconds with common sky view. So so the more common the sky view, the better. But as you get further apart, it gets worse.
I'm just trying to figure out what the drift is mainly driven by. Is this because your signal takes different radio paths, or because you look at two different satellites in the sky?
So they have different. Each has independent. If you have two antennas, they each get independent noise. Like the signal's the same in theory, but they get independent noise. They have slightly different multipath. They have slightly different ionospheric effects. Slightly different. Their own oscillators have their own errors, and so they've done an amazing job of minimizing that. But there's certain physical limitations in terms of how accurate you can get those. Now, you can, if you want to get really fancy, you can get big double oven OCXOs, which can average for a very long time, and all that. That will be more precise. You could lock a rubidium reference or a cesium or a hydrogen maser, and those will get progressively better, but more expensive, and also they take a longer time to average things out. So for example, VLBI, very long baseline interferometry, it's a radio astronomy thing where they have radios on one side of the Earth and another one on the other side of the Earth that are looking at the same star at the same time, and they synchronize through GPS plus hydrogen masers. And so their main reference is their hydrogen maser, and they lock that to GPS at a very, very tight bandwidth. And they're able to record those samples, send them on disks, and they actually mail hard drives around to a central location where they process it days later to do that. But they're able to do it over such a long distance because they're using hydrogen masers, which are 4 or 5 orders of magnitude better than a crystal oscillator. Okay, well, thank you. Oh, we're hiring, so if anybody is interested, you don't necessarily need to be a software radio expert, but is certainly interested in it would help, because that's what we do, quite a bit of software radio. But we're looking for software people, hardware people, FPGA, marketing, whatever. Send me an email or email to jobs@edis.com. And on our careers page, we have some specific openings. But if you're at all interested, just let me know, or you know somebody who is. We would appreciate it. We've got a whole bunch of openings, and we're always looking for great people to work with. Oh, yes. And Jonathan Corrigan is running a training class. So he's been doing training classes, GNU Radio and USRPs for many years, but always he would go to a company and teach 5 or 10 people at that company. Now he has started, in addition to doing that, he's if you don't have the critical mass to get him to come to your company because you only have 1 or 2 people who need training, he's now doing an open training session. So you can go to that. You just sign up. And so there's two upcoming ones. There's one in March on the East Coast in Reston, Virginia, and then one actually right here on April 23rd. It's highly recommended if you it's really the best way to get started doing apps and cool stuff with GNU Radio and usurps really quickly. Okay, so that's at corriganlabs.com.
Okay, thank you, Matt.
Actually, that might make sense. All right. So why don't we just have a 3-minute break, and it will give you an opportunity maybe to use the loo, refill your drink, grab an slice of pizza. I know I completely missed out on pizza, so I'm going to hope that there's something left outside.
Once more with the
I wish for reward myself.
Yeah, exactly. Yeah, I guess there's a couple of factors.
Does anybody know the
Some people have been saying the more jitter you have, and the more bandwidth, the more instantaneous bandwidth, the harder it is. And so, the VLDI is very high bandwidth, it's very high frequency, but I think it's totally extremely long stations that are
Oh, so they have a.
and well, practically, there's no bandwidth filtering, there's sort of jitter. Bandwidth drop is.
Yeah, still some.
I see. So, okay. You were able to get it work here on the low point.
Yeah.
It's probably fine. Actually, for receive performance, other than the bandwidth, it seems to be basically for what I've tried, it seems to be basically the same thing as
Yeah, absolutely.
other than the bandwidth. So on that respect, it's not because like bandwidth, those are good. But I think that it would actually do better than the FPLSDR stuff under certain kinds of worse conditions.
The reason baseline keeps climbing up with each step up efficiency. And so the implication is that we might just be able to drive with that and then go from that up.
Well,
So, if you were to, it depends entirely on what you want to do.
I went to expose for a couple more. I have one of these.
And no matter what you do,
Right, so you gotta get started, start actually dealing with the DSP problems and
multiply out by
whatever it is the configuration.
Bezos goes up by
Figure out,
200.
okay, I want to do
And
something
that's
about
just
the and so, okay, I want to do something about
That's even
why,
with one
why,
PPS at the very beginning.
I mean.
And then you want to take it one jitter. That's a factor of 90.
Okay, I want to
Yes,
Wi-Fi, unless you're
So you
like,
get 180
people sort of, like, possible radio security.
So instead what you do is
not
take out a little bit, and then the
just use it.
filters it down. So you take the one radius
If you're
up to
really
10 megahertz,
enthusiastic
and
about
use the crystal, and
software
you filter it down.
everything. Correct.
And then so,
that's perfectly fine.
and then that with 10 megahertz, then you can multiply it up to 100 megahertz.
There's no perfect
You get
hardware.
it,
You gotta
it's
buy the
much
hardware
more
that
than
needs
that's
it.
that one.
You gotta buy the hardware that does the job that you want.
And then you could filter down with the next crystal.
Well,
Go
there's
to
one-
4 gigahertz, which is now
I
about
have with the exercise.
Okay, so we get 30 or something.
Yeah,
And then you
because,
get
I mean,
filtered.
most of,
filters it down.
most
But
of
the progressive filters are
people
also
are
wide
also
band.
do
That's why you get
any other.
this shape that it starts.
I forget what it is.
The very center is your
Most
master
true.
reference.
Yes. So,
And so it's getting multiplied like that. But then you can then filter for the line filter.
Either
So
if you have recording something and replay,
in the
that's the
system,
thing.
you might not
You know, that you can do that with like several remote controls.
You can only have two.
But that also means that you're transmitting all the original.
But if you were to just multiply PTS straight up.
And there's also few people have done, construct signal and then transmit.
The key point is each oscillators of higher frequencies get higher Q. For hackers,
Oh, just like-
narrow stuff.
I want to have the same thing so I don't have to scratch around.
And you could go, I mean, I should plot down to 1 hertz, like actually. And that is determined by the type of like.
Or you're.
The hardware is have to, at the 10th of hertz is how good would you get. At the 1 hertz is how good the crystal is. And then all the way down there. 100 megahertz.
Or run two of them.
Well, yeah, that one you gotta do, that one you do full.
And most RFICs just have one PLS slot in their
In
In an IC, it's typically.
range to that,
So actually, chart on my computer. So here I show, first reference that I'll play out. That's what you
can tell this one actually comes out. It's only my phone in my pocket, and I'm like, it's rebooting. Why?
This is all in
Hey, still your cat.
What?
It's
Of course.
similar concept. So this one actually mine doesn't have this. It doesn't. So it can't do a whole different DAC.
Oh, yeah.
Yeah, but API can. They have a link chip. Can do a. Program and a set of
I'm going to get a slide.
yeah, so they haven't even had to basically uses it.
It's a little cool.
I'm not sure if this is entirely appropriate, but it's been on my mind. So I just need.
Like the translation and kind of stuff like the.
I'm seeing the most popular things like.
If I sit down, do people still see me? Because I'm going to be typing on it. And do I need a mic?
So I can only see that.
You can also stand. I don't want to sit all the time. It's just like when I'm typing, at least I have to crouch or something. Or maybe is there a box?
I was going to say. No, I didn't see a light. I still like the idea. I'm more on
So actually, I want very visual access.
Perfecto.
Just hold the VGA cable.
I actually screwed it in.
Here, our
Want me to do an intro?
Yeah. Okay. No, we're not using that All right. Thanks so much. All right, so we might resume now with the final talk of this evening. Neil will do a quick introduction.
Our next speaker is Martin Brown, aka M. Is a longtime GNU Radio contributor and the community manager for the GNU Radio project. After several years of being with the Communications Engineering Lab at the Karlsruhe Institute of Technology, KIT, in Germany and working on GNU Radio and SDR projects, he joined Edis Research, first working from Germany and now for the past 2 weeks working with all the cool kids here in San Francisco. Martin has a PhD from KIT and has a first place medal from the K1 go-kart racing.
Thanks. My proudest achievement. Cool, what a day. Yesterday was St. Patty's, so I wake up with a bit of a buzz on some random guy's couch. And now I'm on TV. Hi, Mom. And this all within 2 weeks of moving to the US. So the land of opportunity. Yeah, so as Neil said, I've been working with the GNU Radio project for a very long time. And one thing that I've always paid a lot of attention to, and what probably earned me the position as the GNU Radio's community manager, is the fact that I really try and make sure that we are accessible to new people, that our tools are actually usable. These are things that I deeply, deeply care about. So this talk will be very different from Matt's talk, not only that I'm using a different presentation software, but also this will probably be the most basic software radio talk that you'll ever hear. And I've actually tried to design it that way that no one watching room, or maybe later on YouTube will have any trouble following this. Because I want to make sure that anyone who's interested to do some software radio work knows how to do that, is not intimidated by the huge task that may lay ahead of him. And this is why I titled my talk, Is SDR Really That Hard? So because people keep saying that, throwing that around, it's super difficult. And I'd like to sort of give that a bit more of a, make that a bit more specific, answer that question, maybe. But if things are difficult, then I'd like to lay out what these things are. So obviously, I'm a GNU Radio fan. So I'm going to gear this talk mainly about GNU Radio. So the other question that I'm trying to address is GNU Radio difficult? What does that even mean? And if we want to do software-defined radio work, which tools do we even have at our disposal? Because I'm pretty sure that not everyone knows what all of these are. Okay, so let's start from scratch. Assume that we have nothing, we maybe have some knowledge, maybe we've ordered a U service in the mail, but other than that, we just have our laptop. Hopefully it's running Linux, that'll make things a little bit easier for you. But let's assume no prior knowledge, anything, all of that. It's just like a clean slate, as I said. So the first step that you'd have to tackle is actually getting GNU Radio. That used to be really, really hard. And we've worked very hard to make that easier. And these days, really, all you need to do is either get the GNU Radio Live DVD, and if you do that, so there's actually on our website, we actually have a very detailed explanation how to get that. So there's an ISO, you burn it onto a USB or even on a DVD. You boot from that, and then you get a running system. You can immediately plug in your USRP, you can start clicking around, building flow graphs. All of these things that are mentioned under getting GNU Radio, they're all already handled. So for a production environment, that's maybe not what you want. So you still want to install GNU Radio, but on most distros nowadays, all you have to do is do apt-get install GNU Radio, or yum install GNU Radio, or I don't know, emerge, whatever the is. So this is, I think, Ubuntu 14.10. You'll see we'll have package versions of GNU Radio 3.7.3. That is not the most recent version, but to get started, that is absolutely fine. So there's one requirement I really, really recommend that you should take care of. Don't go with a 3.6 version, because we changed lots and lots of things, and this was released 2 years ago. So maybe you have an old Ubuntu 12.04 or something. In that case, I don't recommend going down that route. But if you can, do it. It's really easy. Now, that may not always work. I'm just going to assume that the source build means something to you. It just means that we take the source code and build it ourselves. If we want to do that, it could be really simple that we download a tarball and we run these commands that are very typical. Like for most software projects, this is sort of how you install them. But we've tried to make even the source build process a bit easier by introducing a tool called PyBombs. Now PyBombs, if you know what apt-get is, think of it, or pip maybe for Python, or npm for JavaScript. So we have that for GNU Radio. It's called PyBombs. So PyBombs was developed by mainly a couple of guys called Tim, I think, but many people have added to this now. And yeah, so actually I'll just show you how it looks like. So this, excuse me. So PyBombs is still under heavy development. So we sort of started tackling that as a new focus, because it still doesn't exactly do what we want it to do. But if you download it, you get something like this. There's a command line tool, PyBombs. So to install GNU Radio, you just run PyBombs install GNU Radio. And so the very first time you run it, you'll have to answer some questions. And most of these you can just use defaults, but it'll also allow you to do things like this, where it can actually install GNU Radio in my home directory. It'll just set it all up. So this is interesting if you're running on a shared environment. So you don't always have administrator access. Maybe you're on some university network. It doesn't worry. I'm just going to install it into my home directory. Do that, and PyBombs takes care of all kinds of things. For example, dependencies. We'll need Boost, for example, or a couple of other things like Cheetah. and it'll try and use your system as well as it can. So in this case, like, so this deb, source means if there's a Debian package, like an apt-get installable package available, it'll choose that. Otherwise, it'll do a source build. So let's use that. And then you can do stuff like, you can say, okay, if you have to do, like, never install boost, like, I'll do that. But you don't have to do that. And this is interesting because, as I already said, GNU Radio is available through apt-get. So I don't. But in order to make sure that I do get a source build, I configure PyBombs to always build GNU Radio from source. And then there's a couple of other things. I'll not go into these in detail. Yeah, you know, like, do I want to build docs? Yeah, why not? Let's build docs. And which compiler insert, et cetera, et cetera, et cetera. And it'll start building. Now, first thing it does is try and figure out what it actually needs to do to install GNU Radio. Turns out it needs UHD. So, okay, here we go. PyBombs comes and installs UHD. And you see it'll download it from the web. This is all, like, you don't actually have to do anything. There's a lot of output coming around here, so I need to come up with stuff to say until we reach the 100% marker. So this is actually cloning the UHD repository that you can find on our GitHub. And I had a lot better speed earlier when I was realizing this. When it's done that, it'll start the. I actually wasn't going to follow through with the installation because I already have it on here, so I'm just going to kill the process here. I'm going to get. Oh, maybe. Yeah. Okay. It's hurrying up. Yeah, you'll see it'll jump into a configuration process and it'll start building it, and once that's built, it'll go into the next dependency, Cairo, and then it'll actually install GNU Radio, et cetera, et cetera, et cetera, and then you have a GNU Radio.
Yeah, so sometimes if you have some pre-installed packages, like, I mean, I've seen it like where you kind of run into impossible situations like that.
Well, I doubt you'll run into impossible situations, but there might be situations where PyBombs can't sort it out.
From PyBombs' point of view, again.
You know, in that case, that's why we have these flags where you just like, just don't install that. Assume package X is already installed. I mean, the neat thing about PyBombs isn't really that, I mean, that is the one neat thing about PyBombs, that it resolves dependencies for you. But the other thing is that we actually use this for the community to distribute their content, right? So,
no, I mean, like, I use PyBombs, but prior to that, let's say I installed GNU Radio and installed some packages. I don't know which versions, like, but some versions of packages. And when I try to use PyBombs, like, it complains about dependencies that were already there, or, you know, but which versions don't match, and then it run impossible.
Okay, that's what I meant by you just override PyBombs just to not do that. Okay, so I'm not going to go to PyBombs customer support. There are definitely bugs in there, and we have a PyBombs bug tracker for that. So, and we like bring it up there, then we'll take care of it. But what I was going to say is like, so it'll install dependencies for you, so you can install GNU Radio very easily. But it'll also do something else, which is it helps us distribute community contributions. So GNU Radio is like one package, but people have used GNU Radio to build other modules. For example, you know, most of the things that we've seen here. Has Nick Foster actually talked at Cyberspectrum? So Nick Foster, like, he has some very, very popular and famous out of tree modules, we call them. For example, AirMode-S. And if you run the graphical PyBombs front end, the App Store, it'll actually show you all of these. So you just click on one of them and it'll install them. This is, I usually don't use this. I prefer the command line. But this gives you a good overview of what we have. So DVB-T for digital TV broadcast, or GR-Phosphor, you know, the very popular visualization tool. So PyBombs, fantastic tool. I'm really happy that we have it. And apart from the App Store, so the App Store is one way to see which tools we have, but there's actually a much, much nicer way, and that is called CGRAD. Excuse me. Now, CGRAD is the Comprehensive GNU Radio Archive Network. So, like, you know, like CPAN or CTAN, like we have CGRAD. And this is actually a new version of CGRAD that we just now developing. It will be released pretty soon. And Cgrant actually passes what's in PyBombs like automatically to generate this website. So this is fully auto-generated. And the nice thing about it is this list of out-of-tree modules. And you can do stuff like search there, so I don't know, like DRM, we're interested in DRM. Oh look, there's actually 2 of these. Let's click onto this, and you'll see like DRM. So Felix, one of the infamous Cells Angels Spectrum occupiers. Yeah, and you can get the repository. It tells you which GNU radio version it needs, and it also lists UHD as a dependency. I think that's actually a fake example, but you get the point. So we have this very nice graphical website that lists all these community contributions like in an easy to browse and just sort of easy to access fashion. So this is going to be coming out very soon. Yeah, Cgrant. So as I mentioned, I didn't actually mention this. So this is how PyBombs knows about the module. Like you write this time, there's just a couple of lines, and in fact, if you write something yourself and you want that to become part of Cgrant and or PyBombs, you send us one of these files, like a couple of lines, and we check it out, see if it's sort of appropriate. If this is like a project that seems well maintained, we add it in, and it'll appear automatically on Cgrant, and people can install it through PyBombs. Okay. Yeah. Any questions about that before I move on? Here. Good. Now, let's say that you have installed GNU Radio successfully, which is now very easy thanks to PyBombs, and you may have installed out-of-tree modules, but you still have no idea how to use all of this. What do you do? No problem. You simply go to our guided tutorials page. Now this is a page, like we had actually a task force to write these, and this was like several iterations of improvement, a lot of vetting, a lot of error checking went into this. So we have like 7 tutorials to go from like absolutely no knowledge about GNU Radio. We assume some knowledge, some engineering knowledge, into like the last tutorial where you actually transmit data over the air, assuming you have some hardware. And I'll actually go into a couple of these just to give you a brief idea how they look like. So like working with GRC, for example, this is, so GRC, the GNU Radio Companion, you must have seen it by now. If not, I'm going to bring it up anyway, is basically the most popular GUI, like the most popular way to get started, which is why we put it at the beginning of these tutorials. And you go through this tutorial, and it'll tell you everything, like how to check out like these extra files that we might need to run the tutorial, because we actually provide an out-of-tree module called GR tutorial, which goes with that. And you don't actually need it, because the whole point of these pages is that it'll help you write your own first out-of-tree module, okay, with its own blocks and everything. And but you can use our GR tutorial basically as a solution. You can know like, oh, that's how I was supposed to do it, and it's all there. You can just compile it. And so this is all very detailed. There's lots of highlighted elements and so on and so on. And if you go into the more advanced tutorials, you'll see other kinds of this is like specific C++ topics, and like PSK symbol demodulation. This will actually teach you some wireless and DSP knowledge. It'll go through explain these pictures, etc. How do I click these together in GNU Radio Companion? And if you like, then you can even skip some of the tutorials. So assuming you're already very, very comfortable with programming and you know everything, no problemo, you just go through these radio tutorials. And maybe it's the other way around. You do some more programming related ones, etc. So we try to focus on the basics. So this is not, we weren't lazy not to make an 8th and a 9th tutorial. We think this is a very good scope. And apart from that, we have many other tutorials on the wiki page which are user contributed, but these are sort of official ones. So we've actually locked those pages, so only admins can edit them at this point. So they become official, and that they stay locked down. So these tutorials talk about GRC, and then inevitably you'll end up using the GNU Radio Companion, which is this fine tool. And I'm pretty sure everyone's seen it at least once. So I was actually tempted not to talk about it at all because it just gets brought up so often. But I thought for the sake of completeness, why not? I'm just going to very briefly iterate through what happens here. So each block has some kind of functionality, and an arrow is sort of a data path. So like this arrow means that this block will generate some data because it doesn't have any inputs, and it'll put it into the next block, and this block puts some data into here, etc., etc., etc. And these GRC files that I have open here are actually part of the tutorials. So this is like something that you could open if you download the GR tutorial out of tree module. So you know, I can just like run one of these, and let me full screen that, and you can see this is sort of an example of a scope output. And these scope outputs are really, really, really important. These are sort of the main reason why you should be using GNU Radio Companion. Why? Well, because when you're writing applications for GNU Radio Companion and debugging them, it's a bit different from a typical C++ workflow where, say, your C++ app doesn't work. I don't know, you put in some printfs, output registers, or you run it with GDB. It doesn't really work that way with streamed real-time data processing because like stuff's happening, like signals are wiggling, you have hardware attached maybe. So the hardware may be acting up. You have no idea like if it's in your software or the hardware. So you need to use the same techniques that engineers have been using on their lab benches for decades now, like scopes and whatever and whatever. The difference being purely in software, we can actually be more flexible than just having scopes. So this is an app that it takes this string. It's like a chat thing. That's why it's called the chat app. So it takes this string and it modulates it digitally, like going back to Kevin's presentation earlier, and then it receives it again, and then it prints the received output down here. Can you just take that, make sure it doesn't buzz all the time? Thanks. So maybe we want to see what's going on. So the problem is, like, if we had a regular scope, then where's my so we want to see the concept of this block. So we just like add it here, kill the app, run it again, so it updates the whole thing. Oh, there it is. So the thing is, like, if I type around, I'm not actually going to see anything. So I can do stuff like I can trigger events that are user defined. So for example, a tag, and I just put it, I think it's what's TSB tag. Oh, yeah, mouse here, mouse. Look, I think I got that right. Yeah. So you can see so this is like the QPSK constellation plot that Karen was talking about earlier, and I just caught that. It's like a very brief burst, but I can just like set this up to find that and then plot these points. And to give you a more complex example, I do not know if any one of you knows what. Some of you probably know what an OFDM is. Some of you might not. So there's a flow graph that receives OFDM, so all kinds of stuff in there. And if I run it, it'll actually work because this is an example that we distribute in GNU Radio. But so if I just run it, it'll actually. I don't have enough screen real estate here. It'll actually output some status information down here, right? So okay, I know it's working, but say it wasn't working, like I'm still writing this and debugging this, then I don't know, my equalizer might. So I can just. I need to find this. I can just drop in one of these again, a constellation plot, connect it to this output, and that's what I meant earlier. We can just like basically put probes anywhere in our digital stream, and you can see this is like a beautiful BPSK output. So I mean, the equalizer might still be broken, but at least it's outputting the right types of signals. So this is, if this wasn't running, this is an error that I've already eliminated. So GNU Radio Companion is like you should always be using it unless it doesn't help, like doesn't exactly fulfill your needs. So for example, you might want to spawn a different depending on the time of day or something. That kind of stuff is difficult to do. in GNU Radio Companion, but you see as much as possible for two reasons. First of all, right on the right, you already have all these blocks listed out. So you can browse them, you can like GUI widgets or equalizers, like they're all sorted here. And if you open the properties, you also get like, this is auto-generated documentation. It doesn't look very beautiful, but it has a lot of stuff in there. Usually is enough for you, if you approximately know what the block does, to fill out the fields. And the second reason is, GNU Radio Companion actually compiles to Python. So if you want to work without GNU Radio Companion, you still might want to use it to generate a file that you can use to sort of see how it all works. So I'm just going to open this in my editor, and you'll see a lot of GNU Radio code. Like here's lots of connect calls, for example. So this is like the arrows are connect calls, etc., etc. And you don't have to watch it. Look at this. But if you do, then it will give you a lot of insight. Okay, so all these blocks, what the hell do they do? So assuming you already know what a frame equalizer is, or a CRC, for example. So I already mentioned that you can actually just open this, have a look at what it says, but you can also go to our manual. And something that we've been improving, and it's actually split up into two parts. So the first part is sort of general usage. This is what you typically find in a manual. So it explains stuff like how to set up a packet data modem, and it has pictures in there, and there's lots of text, and it tries to explain like in a written manner, in a written fashion, how these things work. But you can also use it as a reference in part 2, to find out what the individual blocks do. These are either sorted by the components. This is like how they are laid out in the GNU Radio source tree. So everything in, for example, so the source tree. This is how it looks. No, sorry. This is how it looks like. You have like GR something, and GR digital would be all the digital modulation blocks, for example. So you just click that. Where's digital? There it is. And it'll explain all kinds of concepts that you need to know. Or you can just like go by like directly to the blocks. They are also sorted by different types. And you can just search, of course. You can just do, it's a good multiply. Matrix, for example. You could go here, then it'll sort of give you a description of the matrix multiplier, including all the methods you can call, etc., etc. Now, reading these manual pages is actually, it takes some getting used to, but it's actually explained in the tutorials. So we try and make that as easy as possible. Now, right. The other question, so I kind of gave myself a way out when I said, assuming you already know what a frame equalizer is, then you're fine. So what if you're not, like, what if you don't know how PLL works? So I mean, or I don't know, like a polyphase clock sync. These things, and it's like sample symbol, loop bandwidth. So Matt's talking about loop bandwidth, but maybe you don't know what that is. And taps, Jesus Christ, taps. And then like the documentation won't help you, because it just says like put the taps into here, like for the loop filter, and how do you? There's only one way to do that. So read all of these, and then get the next dash. Read all of those. So I mean, I spent a couple of years at university just getting a degree in digital communications engineering and all of that, and that was not wasted time. So there's a lot to learn. There's no shortcut here. As long as you don't know the basics, you won't be able to use any of this. And this is actually the point in my talk where I have to conclude that SDI is actually quite hard. But it's probably not the, if you get stuck at installing GNU Radio, you shouldn't get stuck there. But if you don't know how to do like forward error correction, like codes, like this is a pretty big book and it's full of math and it's hard stuff. Now, I'd like to say you don't have to know all of these concepts. You can understand forward error correction on a very high level, so it somehow fixes your bits, whatever. So you just drop in a block, a GNU Radio block that does forward error correction. You put in some values that you saw in an example, cross your fingers, and then take care of the rest. if it doesn't work, in a lot of cases, it actually will do something useful. So we actually have a list of suggested reading. I just actually picked these randomly from our library, but these are actually all, and you can see like they're very specific, like phase lock techniques, and multi-rate. There's a whole book just on multi-rate signal processing, like polyphase stuff. You'll take a while to get through that, unless you're studying full time. I think the tools that GNU Radio provides, such as all the widgets, make it actually easier to get to those. Yeah, tutorials already mentioned those, the GNU Radio Companion, and the manual specifically. But now, what happens if I need a block in GNU Radio that doesn't exist? It's not in there yet. We'll have to write that. And we actually try to make that process very, very, very simple for you. So there's a tool called grmod tool, and that'll allow. So I already mentioned out-of-tree modules. Now, out-of-tree modules are extensions for GNU Radio that are not part of GNU Radio itself. It's like I don't know, just like a plugin or whatever. It adds stuff to GNU Radio. And if you want to add stuff to GNU Radio, the best way to do that is an out-of-tree module. So I'm actually going to do some live coding here. So I'm guaranteed to embarrass myself, but here we go. So I'm just going to actually write an entire module for you. And I think hopefully you'll be surprised how easy it is. That's at least my intention. But more likely you'll actually be giggling at my failures. But let's be optimistic. Okay, so I run grmod tool, and I want to create a new module. How do I do that? No idea. Let's run grmod tool help. Oh, great! It actually gives me an explanation of what to do. And I can do grmod tool, help new mod, and it'll just give me different help for this specific command. And this is actually the one I need to create a new module. I'm going to call it cyber, because cyber is in this. What? Oh, there it is. So we have gr cyber here. Gr cyber, I can query if this is actually a out-of-tree module, and yeah, it is. It's called cyber as instructed. And now we need to add some blocks. To have this where we added a block that squared the input. That was our early example. So we're just going to make takes float values and outputs the squared of that. So we run this command, and it'll ask us for arguments. Our block doesn't need arguments. It's just a simple mathematical operation. Yeah, but we'd like some Python code for Q&A. In that case, we don't need any other Q&A code. So let's start editing there. So I'm just going to fire up Vim. You can use other editors as well, if you must. And it'll actually generate these 3 files that we have to edit. And you can see it's already like filled out most of these things. And so this file we don't even have to touch. It just sort of defines our block. It's just like, this is our block. GNU Radio, do whatever you must with it. And this is another file that allows us to add, like private members and all of these things. And because this is a very simple example, I don't even have to edit that file either. So the only file I have to edit is actual signal processing is done. Now you can see these things like these pointy brackets. These are jump markers. I can actually just jump to them. So this way I can I just have to edit the points of the code that are actually interesting. So this tells GNU Radio how many inputs our block has. It's 1, and it's actually a float, and it has 1 output, and it's also float. And we need float pointers if we want to deal with floats. So it's we need more floats. There we are. And then we have this infamous line, do signal processing. And really, this is like where you put your IP or your clever ideas or whatever. Now, we wanted to square that, so we have just put in a for loop because this is C++. So I'm going on these things I explained in the guided tutorials. But so we'll have buffers with a number of items, a number of samples in them. It's called an input items. So we have this a loop counter, etc., etc. And so we know that the output at position E equals the input at position I squared, so multiplied with itself. Actually, I need a int in here. Ta-da! Finishes. My block is done. It's complete. And I can even prove it's done because we have the Q&A infrastructure and so on. So in this file, and this is a Python file that will sort of test my block in a GNU Radio flow graph. So I've actually have some plugins for Vim that help me do all this because I do this a lot. And you can download them from my GitHub. I don't think I have it in my slides, but don't worry. Like through Cyberspectrum website, we'll figure this out. So how do we test this? Well, it's quite easy. We just take a couple of numbers, we push them into our square block, and then we see if the output is actually the square of that. So we need some data. So let's give it some data. Range 4 is Python for give me like a couple of numbers, and then we need a source equals blocks.vector source f data. And this vector, how did I know how to do this? Well, there's lots of examples, and it's also the guided tutorials. But the fact that I know the command line arguments for vector source f is because I use it all the time. But let's say, like my mind slips me, then I can just like use, like most editors have these features where they can just pull up doc strings for Python stuff. It'll do it itself. And once again, it's auto-generated. It's not very nicely marked up, but this is like the function I need to take care of. So data, then we have like, tells us if we want to repeat it, a vector length, and tags, etc., etc. So we only need the data. So we did this correctly. This is our source. Then we have our square block, and it comes from the module cyber because that's the one that we're just writing, square f. And then we need to dump that somewhere else into a vector sync, you might have guessed. We connect these all up, source to square to sync, and then it runs, and then we do a automatic check equal that the output of the sync.data equals, well, I mean, what was it? What do we want it to look like? So it's something like 1, 4, 9. Okay, 9, 9, 9. And I can actually need to set up my build system for this. So this is, once again, we're building from source, our own project. So we need to run CMake, and here you can see that I'm already installing, like I always install GNU Radio to my home directory. I don't do any sudo install. This would completely wreck my workflow. I have like several of these. I can switch between GNU Radio work. So this all, oh, this was the wrong tool. Doesn't matter though. It's just a graphical front end to CMake. I can run make from Vim. This I can't. Okay, it doesn't matter. Let's run it from here. Actually, let's run multiple makes at the same time. It'll be faster. So yeah, so I can just run my unit. Oh, I should be able to run my unit test from here. Doesn't matter. Okay, it doesn't work. I don't know why. 5 minutes ago when I tried it. So we have a test system in place here. Which usually I can run from my editor, but I can also run it from the command line. You can see my unit test failed. Well, that's great because it seems like I have a bug in my code. And so if I can actually see what the bug is by just giving me the output. Why did it pass? Oh no, it's square. There we go. And you can see that range starts at 0. I forgot that. I didn't really forget it. I needed an example. Here it is. So I fixed the unit test to add a 0 in here. In this case, my unit test was broken, not the code, which is usually it's the other way around. That's the whole point of unit tests. But if I ever change my block in the future, I can always test it automatically. Let's go back, see if that works out. Make test, and it's passed. Okay, so this is a block written in C++, and we usually recommend that for performance reasons. But when you're doing research, say you use MATLAB as a workflow, it has a very mathematical-oriented syntax, but it's not very performant and it's a bit clunky. Like writing big complex programs, it's a bit of a hassle. A good compromise is Python. Python is basically as easily learnable and readable as MATLAB. It's also quite fast, not quite as fast as C++, but say we want to add a Python block into here, no problemo. we add a sync block, and I'm not going to explain what that is for brevity, but, and I'm going to, actually, what's a good, any suggestion what kind of block I could make? Has to be easy, because I'm going to write it in under 2 minutes.
I'm interested in CUDA block actually. Like
No, that's too difficult. Quadruple, no, that's boring. We just listen. Okay, I actually have a backup in case no one comes up with a good idea. That's the infamous fizzbuzz. You were?
Yeah,
Okay, I'm gonna give you the credit for that idea. Good choice. -L means I need to specify the language. Actually, if I don't specify language, it'll just ask me, do you want it in C++ or in Python? I'm just used to adding all of these commands. Fizzbuzz, we don't care about arguments. We want some Python Q&A, and here we are. So let's fire up. Actually, I'm going to do the Q&A first, because that's actually how you should be doing it. So, so in my Fizzbuzz, like everything with the 3 in it, or like module 3 will be a fizz, and it has a 5, it'll be a buzz, and it has both Fizzbuzz. So, you know, I'm just going to 1, 2, 3, 4, 5, and so what's the expected output? Neil. Okay, actually, fizz and buzz aren't numbers, so let's give fizz a 1 and buzz a 2 and fizzbuzz a 3. So what do I put in here?
1, 2, 1.
1, 2, 1. So like it'll be 6 outputs, 1 for each number. Okay. So 0 is not a fizz nor a buzz. 1 is not a fizz nor a buzz. 2, near. 3 is a fizz, and 4 is nothing, so it's 0, and 2 is 2 is a fizz. Okay. And we do the same thing as before. So actually, I'm so incredibly lazy. I'm just going to copy that from here. And that is fine. You know, look at all the examples. GNU Radio is open source after all. There's so many resources to work with. So here we have to do it a bit differently. We can't directly access the module yet because we actually haven't installed it, because the QA infrastructure does all of this without installing it. Connect these up. And we have source, fizzbuzz, and we figure out what? That better? Yeah, Moritz is our white space chaperone. And we check that the output matches the expected output. Now, if I run the unit test, what will happen? Okay, Barn, what will happen? Yeah, of course, I haven't written the block yet. Why doesn't it fail? Ah, demos! Oh no, I need to run CMake again, or make. I can never remember. Probably make. Yeah, even make fails because the Python is not valid. Fizzbuzz. Okay, who knows how to write a fizzbuzz? Okay, first of all, I need to declare to GNU Radio what this block does, and it takes floats in and it outputs floats, and floats have 32 bits. So there we are. So now we have two vectors, in 0 and out, and in 0 has our input, and out is where we write the output. So enumerate. So we enumerate the input, and okay, Julian, give me the codes. What do I write here? So actually, I'm probably doing something like this because I'm writing to the vector position index equals.
That is a good question.
Okay. So I have a. So what I have to do is I actually, whoops, getting ahead of myself. I initialize it to 0, and then if the input in is actually a keyword in Python, so I can't name my data in. That's why it's in 0. 3 equals 0. This is a 1. Okay. 5. Actually, we increase it by 1 because, you know, otherwise we don't get a fizz buzz. Okay? Julian, is that fine?
Plus 2, except for 0 in the test case.
Except for 0 in the test case. Sorry, what?
0 in the test case is also 0 mod 3 and 0 mod 5.
You are a smart guy. So what do? We just test for 0?
It doesn't count as a fizz buzz.
Let's count it as a fizz buzz, but thanks for pointing that out. Actually, it really doesn't matter. I just needed a block that I could code up in. So this is the same line, signal processing. I can jump here, delete that, and there we go. So this is our block. Let's see if it runs. Fingers crossed. Didn't work. I don't know. Actually, this was supposed to fail.
Yes, because
I failed my own test. Oh yeah, of course, right. Because exactly what you just said. Okay. Right. I'm gonna kill this anyway, but let's. That is 3. Yeah, so it's the fizz buzz. So I'll, you know, there we are. Phew. So did I pass? That's how we write blocks. Now tell me that's not easy. I mean, you know, I failed at the fizzbuzz algorithm, but you know, had I known better, I would have gotten it right. So, because the actual infrastructure provided is really, really simple to use. Okay, and let's say I want to pull this into GNU Radio Companion. Then there's actually some tricks I can do. I can use grmodule, for example, to auto-generate an XML file for the square block. And it says, like, this is an experimental feature. It might work, might not. And there's already an XML file for GRC. You really want to overwrite that? And I'll go, yeah, sure. And go build, and make install. And fingers crossed, if I reload the blocks, then I should have Cyber. There we are, look, Cyber. Actually, I probably installed it earlier for, oh, this is the fizz, but oh, yeah, right. Okay, so the square, we can just like drop it in somewhere, and we can already use it. So this will square something. Do you have something that can be squared? I think it has something here. Yeah, let's use that. So this gives me a ramp, and I'm just gonna put in the square. And I'm pretty confident it'll work because the unit test worked out fine, right? Ta-da! There we are, square. Okay, so assuming you should be able to write the codes, no excuses. Unless we can improve that, and we're always open for feedback. Are there any questions about this process? Neil?
Just a comment, you mentioned all those books and different resources and things like that. Maybe we should mention the GNU Radio suggested reading page as a resource.
Yeah, I did actually sort of mention it in a somewhere, but yeah. So I have a list of like websites that I wanted to recommend, and I actually should have put that in there. So, but on the wiki page, there's suggested reading, and there's also another suggested reading order, I think it's called, because the suggested reading page is so long at this point. But like even with all of those pieces of information, you might still not be able to like answer all those questions. And seriously, who can? Like, this is all very difficult. Like, we cannot do this by ourselves. So there's lots of ways to get help. There's the mailing list, for example. So the mailing list is very active and usually very helpful. You can see like anything with a number here. I mean, you know how Gmail works. It has a response. So only like the very earliest ones haven't been answered yet. And there's a good community of people, very smart people, like to help. Yeah, so mailing lists, and also there's all kinds of announcements there. So it's a good place to be if you're in the software radio world. Also, we have Stack Overflow. So Stack Overflow, Kevin mentioned it. This is sort of, you use Stack Overflow if you have a very specific question, and you expect that to be a good answer to it, and it's supposed to be Google indexed. So this is something if you're having a discussion, the mailing list is better for that. Simple question and you're expecting some answer. This will work fine, and then usually Marcus answers the question most of the time. And there is actually an answer, right? Of course, Marcus writes an answer. And of course, if you still aren't satisfied with the amount of community you're getting from us, there's IRC. And I can actually, hey guys, talking live at Cyberspectrum. Yeah, so a lot of people in here. So sometimes, so this doesn't always give you actually help. You know, sometimes you ask a question that people get derailed and they talk about, I don't know, whatever. But it's a fun place. It's a fun place to hang out. And of course, there's Cyberspectrum, etc., etc. So we have all kinds of things going on for you. Now, finally, say you aren't satisfied just writing it out of 3 modules, but GNU Radio itself, a feature that you think is actually a core feature, like you might have it in the out of 3 module, but you think this should be in GNU Radio. You're gonna give it to us. I mean, not to us, give it to the GNU Radio project. Or even, bad documentation. Like that is very easy to change. Like say you're figuring out how block works. That's the perfect time to write documentation, because that's like when you have the like you've gone from no understanding to I've got it. That's the best time to write documentation. Like years later, when you can do it in your sleep, you won't be able to write good documentation unless you're a professional technical writer. And even if there's blocks that are written in a manner that you just can't understand the code and you think you have a better solution that might even be more performant, we love all of that. Now there's one, I don't want to call it a caveat, but there's one thing I want to point out. If you have big contributions into GNU Radio, you must transfer the copyright to the Free Software Foundation. This is just to make sure that no one sues us and says, oh, this is actually my IP. So something like on the order of 10 lines or more, like or anything that's bigger. I think with documentation we can also be a bit more lenient. You will have to like one time sign a thing, telling us that anything you write in upstream, you don't claim copyright. Now there's actually, sorry, I wanted to bring this up earlier for the mailing list. We actually have if you're new to mailing lists and IRC and whatever, have a look at this page. It seems like a big read, but it just gives you so much more out of the communication, the interaction. Because a lot of people, we sometimes get emails on the mailing list that are, people haven't put in the right amount of thought. And now this is, I'm not saying that people do this to piss anyone off or, out of any bad reason, but it burns out volunteers who help on the mailing list. Okay, so, if you just like go through this, and you'll have them internalized very soon before you write an email, like the whole mailing list is productive. There's actually 2 mailing lists. I should have mentioned that earlier. There's Discuss GNU Radio and there's USUP users. And Discuss GNU Radio is more about GNU Radio and USUP users is more about USUPs. But there's huge overlap, and it's not like there's a boundary between those. But there's different people on different mailing lists, so you might be, if you have a very GNU Radio specific question, you're just more likely to get a good answer if you go to Discuss GNU Radio. Now coming back to the improvements on GNU Radio itself, we have the issue tracker, and this doesn't only track bugs, but also like new features. So you can see Sebastian here, one of our GRC gurus. Like he has a couple of upcoming features, so he's actually listed them here, so you can see what's going on, and you can actually like help him debug them. But of course, the main use of this tracker is actually the bugs. So something like GUI glitches or whatever. So sync decimator FF block gives decimation above 262,000 gives segfault. So this was a bug. It must have been in there for 10 years, but no one runs a decimator at this decimation because it's crazy. But it's a bug. It needs to get fixed, and it's in the list. And so this is a good place to start. So if you have a bug, you can't fix it yourself, go post it here. You want to fix something, but you don't actually have a bug, go here. Find something, fix it, upstream it. And how to upstream it is all explained on this FAQ, which is specific to contributors. We also have a more general FAQ. This is sort of all the questions that come up a lot. This is stuff that could also be on Stack Overflow, but we've had the FAQ for a long time now. So say you've written some code, you've followed all these guidelines. Next step is pushing it to GitHub. That's the easiest way. Submitting a pull request. You don't have to do that, but it's really recommended. And you can see like there's a couple of outstanding pull requests. That's because someone has to triage them. Some are actually like marked hold. That's, for example, this is something that we might put into the next version, but we don't want to merge it right now, so we just keep it here for future purposes. And Jonathan or Tom will then eventually merge these things, or maybe give you feedback why they're not getting merged. Okay, so that's that. Now, I already mentioned the community aspect. So you're not supposed to do all this alone. Like, find other people who are doing stuff. There's a conference where you can meet people, like-minded software, radio, open source enthusiasts. This year's conference probably will be around the end of August. There's more information going to be following. Also, local meetings. And if you don't have local meetings, go organize them. No problem. And advertise them on the mailing list. So we have a couple of people doing that. And what's this thing about clothes? Well, we also have our swag shop. It's just something I wanted to bring up, get the t-shirt, and of course, the orange coffee mug. Radio is there in all situations. And yeah, stuff, you can buy stuff. I think that is it for now. Now, did I answer the question, is SDR hard? I think it's pretty obvious that there's no arguing that software-defined radio is hard. There's no way to getting out of that. Is radio hard? I don't think so. It could be better, but we're working on it, and if you help us, then it will get better even faster, and it will get even better. And also the fact that there's like millions and millions of books that you can read on software radio and everything that's related, wireless propagation and coding, and even all the the programming aspects, like multi-threading and FPGA dev, whatever. There's so many things, you name it. Like none of that should discourage you from just getting started and doing some software radio yourself. So because GNU Radio already provides a lot of these things, you can actually get very far, just by focusing on one little item. So there's that one block you need to learn about. Okay, just learn that, add it in, and try the rest and see if it works. And that way you'll be progressing, you'll be learning, maybe in baby steps, but at every step you'll be having lots of fun, and you'll be seeing output, and there'll be scopes and lines wiggling across your screen, and FFTs rendered in OpenGL that look really, really beautiful. Really, there's no excuse not to get started with software radio. The software doesn't cost anything. You just need a laptop, maybe some hardware to receive IQ data. Yeah, that's it for now. So any more questions? Can be more general GNU Radio. I'm happy to answer them all. Well, it's 10 o'clock. I wouldn't be offended if there's no more questions. Okay, well then, thank you very much. And
thank you very much, Martin. I think that was very informative. I even learned some stuff.
Really?
So yes, thanks all for coming. Thank you for joining online. And we will have hopefully our next one at the end of April. So look forward to seeing you then up in San Francisco.
29.
On the 29th. That's the tentative date anyway. And we'll be posting these materials on the Meetup page. And if you like GNU Radio at all, then definitely check out the resources that Martin has talked about, and we will post those links up there as well. So thank you very much and good night.
how long do they